Welcome back to the show. Today, we're diving into the intriguing world of distributed systems, specifically focusing on the CAP theorem and what it means for consistency models. If you've ever been curious about how systems maintain reliability and performance despite network faults, you're in the right place. We'll explore the nuances of consistency, availability, and partition tolerance, and discuss why the CAP theorem might not be as straightforward as it seems. So, grab your headphones and let's get started. To kick things off, let's clarify what the CAP theorem really is. At its core, the CAP theorem states that in a distributed system, you can guarantee only 2 out of 3 properties at any given time: consistency, availability, and partition tolerance. But here's the twist. This framing can be a bit misleading. Network partitions or faults are inevitable. They're going to happen regardless of how you design your system. A more accurate way to think about CAP is consistent or available when partitioned. This shift emphasizes that when a network fault occurs, you must choose between consistency and availability. Now let's unpack availability a bit. There's a lot of confusion surrounding this term. The formal definition of availability in the context of the CAP theorem doesn't always match our everyday understanding. Many systems marketed as highly available might not actually meet the CAP theorem's strict criteria for availability. This discrepancy can lead to misunderstandings about the true nature of distributed systems. In fact, some experts even argue that we should move away from the CAP theorem altogether, as it doesn't offer much practical guidance for designing systems. Another important point to consider is that the CAP theorem has a rather narrow focus. It only looks at one type of consistency model, linearizability, and one type of fault, network partitions. It overlooks other factors, like network delays or nodes that are alive but disconnected. Because of this, while the CAP theorem holds historical significance, it lacks practical value for modern system design. There are other findings in distributed systems that provide a clearer understanding of what's achievable and what's not. Speaking of linearizability, let's see how it plays out in real-world scenarios. Interestingly, even something as fundamental as RAM on a modern multi-core CPU isn't linearizable. When one thread writes to a memory address, another thread reading that address shortly after might not see the updated value unless specific measures, like memory barriers, are put in place. This leads us to the concepts of store buffers and caching. Typically, memory access goes to the cache first, with changes being asynchronously written to main memory. This can result in multiple copies of data existing at the same time, ultimately leading to a loss of linearizability. So why do we make these trade-offs? It's not just about fault tolerance, it's really about performance. The CAP theorem shouldn't be used to justify the multi-core memory consistency model because within a single computer, we expect reliable communication. If one CPU core becomes disconnected, the whole system's operation is compromised. The decision to forego linearizability is driven by the need for speed, not a desire for fault tolerance. Now let's tackle a common question. Can we find a more efficient way to implement linearizable storage? Unfortunately, research suggests that the answer is no. If you want linearizability, the response time for read and write requests must be at least proportional to the uncertainty of network delays. In networks with highly variable delays, like most computer networks, this means that the response time for linearizable operations will inevitably be high. In contrast, weaker consistency models can significantly speed things up, making this trade-off crucial for latency-sensitive systems. As we delve deeper into consistency models, we encounter the concept of ordering. In distributed systems, understanding the order of operations is essential. For instance, in single-leader replication, the leader determines the order of writes in the replication log. Without a single leader, conflicts can arise due to concurrent operations. This brings us to serializability, which ensures that transactions behave as if they were executed in a sequential order, either by executing them in that order or by preventing conflicts through locking or aborting. Another key aspect we need to consider is causality. Causality helps us understand the relationships between events in a distributed system. If one operation depends on another, there's a causal relationship between them. This concept is vital for maintaining consistency in systems. When a system adheres to the ordering imposed by causality, we describe it as causally consistent. Snapshot isolation is one way to achieve this, ensuring that when you read from the database, you see data that causally precedes any data you observe. To illustrate this further, let's compare total orders and partial orders. In a total order, you can always determine which of two events happened first. For example, natural numbers are totally ordered. You can easily say that 13 is greater than 5. However, mathematical sets are not totally ordered. For instance, you can't compare the sets A, B, and BC directly because neither is a subset of the other. This distinction reflects how different database consistency models operate. In a linearizable data store, operations must be totally ordered, meaning there can be no concurrency. Conversely, in systems that allow for concurrent operations, we see a partial order where some events are ordered while others are not. This brings us back to the importance of understanding causality in distributed systems. Causality defines a partial order of events. One event leads to another. If a system respects this causal order, it can maintain consistency and avoid confusion. For instance, if Alice shares the score of a football game, Bob should also be able to see that score shortly after. If he doesn't, it creates a violation of causality, leading to confusion and inconsistency. In conclusion, the CAP theorem and the concepts of consistency and causality are fundamental to understanding distributed systems. While the CAP theorem offers a framework for thinking about trade-offs, its limitations highlight the need for a more nuanced understanding of system design. As we continue to explore these topics, we'll uncover more about how to build reliable and efficient distributed systems without sacrificing performance. Thanks for tuning in today. If you enjoyed this episode, don't forget to subscribe and join us next time as we dive even deeper into the fascinating world of distributed computing.